Section 3.3, we're going to take a look at subtraction of whole numbers. The first thing we're going to do is look at a definition of subtraction defined in terms of addition. So for any whole numbers a and b, where a is greater than or equal to b, a minus b is the unique whole number c, such that b plus c is equal to a. And in as much as sometimes we feel like definitions feel a little bit bulky, this one's pretty good. And the reason it's pretty good is because this is usually how you talk about subtraction to small children who've learned addition already, is that you talk about the fact that if you're trying to do 3 minus 2, you ask yourselves, how much do I have to add to 2 to get 3? And so you say something like this, 2 plus what is equal to 3, right? That's all this definition is saying, is that subtraction is this idea of this finding this missing piece. It gets me back to the first number. So this is a pretty good definition. We have three different models for subtraction. So the first I'm going to show you what those models are, and then I'm going to have you find some people around you. We're going to split up into groups kind of early today. And we're going to take a look at creating different problems using these kind of models for subtraction. So the first model for subtraction is the one that people tend to gravitate toward when they think about subtraction. And that is the idea that subtraction is takeaway. So this is the takeaway model for subtraction. Abby had 24 rocks. Eli sneaked into her room and took 5 of her rocks. How many rocks does Abby have now? So in order for it to be a takeaway model, you have something and you're removing something from it. Okay? You have something already and you're removing something from it. So if we're modeling this from a concrete standpoint, we might actually draw out 24 rocks. So I'm going to draw that out. And there's 6. We'll copy paste. Okay, here's our 24 rocks. And then we're taking away 5 because Eli sneaked in and took 5. So we have this idea of them being physically removed from the situation. And if we were to count up the number that were left, we would find that we have 19, get the right number there, 19 rocks left over. So takeaway means I have it and I'm removing something from it. That's not the only way that we talk about subtraction. In fact, the next one is one that I've already mentioned today is quite different. This is the missing Addins model. So in the missing Addins model, you have something, but you need something more. You're missing something to make something work, like Lilise. Lilise needs to collect 10 leaves for a school project. She and Temeskin go out and find 8 leaves. Right? They didn't have 2 and then 2 got taken away, or 10 and 2 got taken away, like in the situation with Abby and Eli. They need something, they just don't quite have all of what they need. There's something that's missing. How many more do they need? So when you're drawing this, the way that you would draw it, and I'll change it to green just because I can, we're going to draw our 8 leaves that we have. So here's 1, 2, 3, 4, 5. So here's the 8 that they have, right? They've collected 8. And what we do is we draw in the missing ones as dotted images showing that we don't quite have them, but we need them. So they're not there. They need to be there. They are currently missing. And the number that we would count is actually the number that are missing instead of the number that we have removed like we did, or that were left over like we did last time. So we need 2 leaves. So this again is a concrete picture of how to do this, but we don't have to do it from that perspective. You can also do it from the additions definition that we saw before, where we saw this and we said, okay, well I have 8 and I'm missing something to get up to 10, right? And then I'm looking for what fills in the gap to be missing. It's 2. So the number is 2 leaves. So you can think of it more from like a missing piece of an equation standpoint. And you do see equations written like this a lot more at younger ages these days, getting that idea of equations into the process of thinking mathematically earlier on. So you'll see this be more commonly used. Okay, I have one more. And I also am going to mention that there's one that your book took out when they changed this edition, which is sort of unfortunate because it is an additional model for subtraction that's a really good one. But let me show you the last one that they show right now. This is a number line or measurement model. So Akeem drives 15 miles to the mall. He's on his way home, and his mom calls to ask him where he is. He states that he's coming home, and he's driven 8 miles so far. How far is Akeem from home? The primary thing that sets this description apart from the other two is that this one is something that's measured, whereas the other items were things that were counted. We count the leaves. We count the rocks. But we measure distances, right? You can do other objects that are measurements too. Like think about measuring like a measuring cup, right? It isn't that we aren't going to use, it's not that we're using decimals or fractions. We're not doing that. But it's something that we measure as opposed to something that we count. Okay? So for this one, what we're going to do is we're going to draw a picture. Again, a concrete picture of how to do it. Not the only way to do it, but it works pretty nicely. And so we have here is Akeem, and this is his home. And over here is the mall. And the distance between home and mall is 15 miles. And then part way back, Mom calls Akeem. And it doesn't even matter that it's like appropriately in the right place. It's somewhere in between. Just make your mark in between. Doesn't matter where you make it. And when she calls him, he says he's gone how far? 8 miles. And so the question becomes, how far does he have left to drive? So what would have to go in this location for it to be the same value as the 15 marked on bottom? 15 minus 8, which is 7. So 7 miles is our answer. 15 minus 8, you can think about it from a perspective of missing addends, kind of like the last one too. What's missing to get up to 15? But the answer is 7 miles. Okay, so here's what you're going to do, and we're going to do this when we get to multiplication as well. I think that we would have done it with addition and subtraction, or addition, but we ran out of time. So we're going to do this, at least for sure, we're going to do this with the subtraction one we'll do today. So I think I had new group works for you, people for you. Let me see just a sec. Okay, so once you've shifted, found your person, resituated your stuff, what we're going to do, oh, and I didn't mention it. Let me actually mention this one. The one model that got removed, which I think is unfortunate because it's actually a really good model, is called the comparison model. The comparison model is the idea that we don't take away, we don't add in. It's just simply asking the question of how far apart things are. For example, if Jill went out and shot 15 baskets and Joe went out and shot 12 baskets, how many more baskets did Jill shoot than Joe? Right? You're not taking anything away. It's not subtraction like that. You're not missing adding. It's not a measurement model. It is something completely different, and it got removed from your book. But I want you to be aware of the fact that that is another model for subtraction, and questions do come like that, but they don't sound the same, right? That question does not sound like any of the other versions that we had. Okay, so what I'm going to have you do then is I want you and your partner to create, this should say 3, a word problem for each of the 3 models for subtraction, since your book eliminated one. So you're going to create a word problem for the takeaway model, a word problem for the missing addends model, and a word problem for the number line model. Okay? So you don't necessarily have to solve it, you're just creating the problem. Okay, you sure? You're writing a question, which sounds like something I'd ask you to do on a test possibly, right? Mm-hmm. Yeah, it does. It's probably a good idea. Yeah, yeah. How about your 3? Okay. Do you have your 3, Kaylee?
No.
You're on the third one?
Yeah.
Okay. Autumn, what are you about you guys?
We're on.
Okay, cool.
Yeah.
No, you're fine. No rush.
Yeah, let's yeah. Those were sometimes my favorite questions on the test because I could just pull out whatever.
Okay. That's good.
Sometimes I like to use the people in my life and then they feel honored when I tell them after the test, like, hey, I brought a question about you.
Well, you'll notice 4 of my children were just listed in
All
my
of these real life
questions.
problems.
Well, there was a leaf project once upon a time, and my daughter Abby did really like rocks at one point, so
It's possible.
it's definitely possible.
Are we gonna solve each other's problems?
We're not. Yeah. We are going to share, though.
How much is
Okay, I need a volunteer. Somebody tell me what you wrote down for your takeaway model.
We got it.
All right, what do you have, Kinsey?
We said Sammy has 30 Skittles. John comes and takes 12 of Sammy's Skittles. How many Skittles are left?
Oh, we have missing Skittles. That's so sad. It's tragic. All right, somebody, one of you guys, somebody tell me your one for, I almost said your one for Skittles. That's not what I meant. One for takeaway is what I meant.
Emma had 18 cookies and Tom ate 11 of them. How many cookies does Emma have left?
Good. All right, so we have cookies. So in all these examples, you should have something and then something gets removed from those something. Okay, so at the back, Lisa and Autumn. One of you, read me your missing add-ins, one that you chose.
We said Robert needs 5 suckers to give to each of his friends. He has 3 so far. How many more suckers does he need?
Excellent. So he has something, but not quite enough of it, and then he's figuring out how many more he needs. All right, so of our last 2 groups, somebody read me your missing add-ins one.
I can.
Okay.
Brooke needs 12 buttons for a dress. She found 7. How many buttons does she need?
All right, buttons for a dress. Yeah, that's good. And these are good small numbers, which is where we're starting with when talking about this too, so that's good. All right, so then you guys, each of you, tell me your number line measurement one.
Jack lives 10 miles from the park and he drives 3 miles back. How much farther does he have to drive until he gets home?
Okay, so we're driving miles from the park to home and so forth, and what do you have for yours?
The Talbot Olive Friends, Farmer Joe's friend, found him 12 miles down the road. Farmer Joe's friend called him, he was 6 miles away, how many miles in the
All right, miles on the road. And while we've used distances, and the one that I gave as a distance, it doesn't have to be that either, right? So it can be other things that can be measured. So it could be like yards of fabric, kind of in your idea about your buttons, right? Or it could be cups of sugar in, a recipe, or teaspoons of sugar in a recipe, something like that. So it's a measurement thing too. So it doesn't just have to be miles. Okay, we good with that? All right, so I was checking my notes while you guys were doing that too. We are going to do this same process again in sections 3, 4, and 3, 5. I knew there's 2 more sections that we had. I just couldn't remember if it was the one we already did and we skipped it or not. We didn't. So 3, 4, and 3, 5. All right, so moving into the next piece is going to look like, as we move through this section, at least if you remember back from before spring break, it's going to look like what we did in section 3.3 or 3.2, where we encountered each of these topics along the way. It's just that there's just this sort of different twist on it because we're looking at subtraction now instead of looking at addition. So these are the properties. So these were the four properties that we had with addition. We had the closure property, the commutative property, the associative property, and the identity property. And they all held for addition. They all existed and they all worked. So what we're trying to decide now is if we still have the whole numbers, okay, that's still our set of numbers, will subtraction work to keep these properties in place as well? So the first one is closure. So if you'll remember, the way we talked about closure, and we did it in our questions this morning too, or at the beginning as well, closure means you take two objects from the set, and the set we're talking about are whole numbers, and you use the operation mentioned. Now we're using subtraction. And the question is, will you always get another object in that set, namely a whole number? So if I take two whole numbers and I subtract them, do I get a whole number? Always. Okay, give me an example of one you're thinking of that works. Kenzie? 4 minus 2 is 2. Yeah, definitely. Whole number minus whole number gives you a whole number. Can you think of one that doesn't work? 2 minus 3 doesn't work. And all it takes to break the process that the property holding is one example where it doesn't hold. So there is not a closure property, and we will use the example that Kaylee gave. If I have 2 minus 3, I get -1, and -1 is not an element of the whole numbers. We've seen those symbols before, right? Not an element of the whole numbers. Commutative. Commutative means we can switch the order. We did this with addition, right? We had things like 2 plus 3 is the same as 3 plus 2. Now, can we do that with subtraction? No. Can you give me an example?
2 minus 3 and 3 minus 2.
Right. We use the same one we did before. So 3 minus 2 would have been just fine for the first property if that were an example we were using, right? But if I switch it, it does not yield the same quantity. It's the same number, but it's not the same sign, and the sign matters. 2 minus 3 and 3 minus 2 are not the same value. So there is no commutative property. You can't switch numbers around for subtraction the way you can for addition. Associative. Associative is a little bit harder to work with, but we'll use your same 3s and 2s that you guys had before just to do that as an example. If I did, so the answer is going to be no. If I did 3 minus 2, and then I did -1, will that be the same as doing 3 minus and doing 2 minus 1? So let's do the left-hand side together. What is 3 minus 2? 1, and 1 minus 1 would be 0. On the right-hand side, I have to start in the parentheses. What's 2 minus 1? 1. And then on the outside, the 3 minus the 1 would give me a 2. So this does not hold, which means the original one didn't either. I can't just put those parentheses in anywhere. Where they are matters, and it will change the value. So no associative property. Identity. The identity property for addition was that we had a number, namely 0. And when I added that 0 to anything, the number didn't change, right? So 5 plus 0 or 0 plus 5 are both 5. It still ends up being 5. Do I have an identity for subtraction? What do you have in mind, Kaylee?
Wait, you can't subtract 0.
You can subtract 0. So if I did 5 minus 0, what would I get? 5. So 0 is the best contender because it works that direction anyway. What happens if I switch the order? Now I have 0 minus 5. And what's 0 minus 5? -5. It's not 5, right? So it's like, there's no such thing as what I'm going to tell you, but it's almost like it's a half identity. There's no such thing as half identities, but it works half the time, right? It works half the time, but it needs to work all the time. So we can give as an example, 5 minus 0 equals 5, and that sort of checks out. Yay, it worked. But if I switch it around, 0 minus 5 does not equal 5, and so it fails. So we just learned that there are no properties for subtraction. So sad. No properties work. They all worked for addition, and none of them work for subtraction. The next thing we're going to look at are algorithms. So algorithms, if you'll remember, are just ways that we can go about doing things. And many of these are going to feel very familiar. You've seen them before. We're just doing them with subtraction now instead of with addition. The first one is called the concrete model. We've got 34 minus 18. And the concrete model, what we did is we actually drew a picture. If you were using this with children first early on, you would actually give them manipulatives and they would do it, right? Like you'd give them the blocks. These are the base 10 block ones where you'd have 3 of these longs. All right, so they'd have 34. There's 3 longs, and then they'd have 4 little squares, like so. Yeah. So 34. And then you are thinking about it very much in a takeaway kind of a process. I have these objects, I'm going to take away 18. Well, it's easy enough to take away the 1 part of the 18. That's 1 long. But the 8 means I should be taking away 8 of the little units, and I don't have 8 units. So what do I have to do? Well, I have to take one of those longs and I have to break it apart like the Legos, right? You need to break that piece into its individual units. So there's some sort of a change that's going over here where I have to change this into ten individual units rather. So there's 8 of them, 9, 10. So I've taken them and I've broken one of the longs apart, and then I'm going to remove. So I'm removing one of these, right? One of the longs. 18 means 1 long, and 8 units. So here's 8 more that I'm removing. And so what that leaves me with then is one of these longs that's still intact. And I have these units here at the end that are left. How many of them are there? 6. And so this is sort of like the next step in the process. And I have 16. 1 long, 6 units. And this is the tactile learner people, right? They can touch and feel. You can break apart the stick of Legos. And this one works it works best if you have the ability truly to break them apart. Could you do it with paper? You could do this with paper, sure. You give them a whole bunch of long strips, and they can cut them apart, can they not? You got to keep track of all the little pieces. But they can cut them all apart, and they could physically move things out, right? They could do that. And so this is very easy to do low budget. Even if you don't have the Lego blocks that break them apart, you can do it with paper. What do you think? It's okay, right? It's okay. All right, let's look at another one. So the standard algorithm, that's the one you're most familiar with. It involves something that you've probably called borrowing. Current terminology uses the phrase regrouping instead. So what we would say is something like this. First of all, this algorithm works from right to left. So we start on the right-hand side, and we'd say 4 minus 8. And a very common mistake is that some child is probably going to do 8 minus 4, just do big minus small. I still, 2 children in my house that still do this. And one of them's in 8th grade, because they just look at it and they get going quick, right? It's not that they don't know. They just get going quick. So you really have to emphasize that it's the top value minus the bottom one. When they flip it around, they're trying to do some kind of a commutative property, which works for addition, right? If I were doing addition, 4 plus 8 or 8 plus 4, I'd be totally cool. But you can't do that with subtraction. All right, so I have to be able to look at this and say 4 minus 8 and say that's not enough. I can't do 4 minus 8. So what I have to do is I have to take one of these from the next column away, and I have to regroup it in my column in the ones place. So now I have a 14 instead of a 4 because I've borrowed or regrouped 1 10 and made it into 10 ones. And then I can do subtraction as I've done before. 14 minus 8 would be 6, and then 2 minus 1 would be the 1. Things that are a little bit tricky about this, first of all, the moving right to left can be tricky. Second of all, the commutative, flipping it upside down, just doing big minus small can be a little tricky for kids. Another thing that can get kind of messy is that you have to write that 14 in pretty small, or sometimes people will do this. What am I doing? Subtraction of 18. Is that they do this and they write a 2 and they write the 1 right here, and it starts to merge together and it doesn't look real clear, right? So there's some sort of messiness going on with the notation. Obviously, the way that I did it with the red was purposeful because I wanted to draw attention to you of what I was doing, right? But usually that's not what happens when you're writing this down. You're writing in pencil. So the attention is a little bit lost there. So it's not that it's a bad method. It's the method that we've standardly used. You know, that's fine. But it sort of has some nuances that make it a little bit messy or tricky for our kids. So kind of a blend between the concrete algorithm and the standard algorithm is the expanded algorithm. And again, we saw this one as well with addition. So this idea is breaking them apart by the tens place. So I have a 34, so I've written it as 30 plus 4. And I have the 18, which is written as minus 10 and minus 8. Okay, so you have to subtract both pieces. So what happens when I do this one is that when I do the regrouping, I can see that from the 30, I'm changing it to a 20, and I can actually see where 10 of the numbers are coming from. Do you see that? It doesn't look like I took away 1. Over here, when I changed 3 into 2, it looks like I took away a 1 and added a 10. That's what it looks like. But that's because it's in the place value. That 3 is the 10's place. It means 30. So when I borrow, I'm really borrowing 10, and I'm just regrouping it over here with the 4. The 10 shifts places. Right? It literally moves from one column to the other column. 10 of them move. And then I can do my subtraction as I'd seen before. 14 minus 8 would be my 6, and 20 minus 10 would be my 10. And then I end up with a 16.
Wait, why did we change 32?
Because we regrouped it. We want to be able to subtract. I can't subtract 4 minus 8. So I need more over there to do the subtraction. I'm shifting it. This is like what happens when you go to the bank and you move money from your savings account into your checking account so you don't bounce that something you just wrote or scanned, right? It's the same thing. It's just shift of funds. Yeah?
We have to put, what is the subtraction in between the 10 and the 8 for?
Because I'm actually subtracting these. It's 14 minus 8.
So then what's the
It's 20 minus 10.
plus sign for?
Do you mean between the 30 and the 4?
Yeah.
Because it was 34. What we're actually seeing happen here, Kaylee, is that when I do 34 minus 18, I have to subtract the 1 and I have to subtract the 8 both. So when I break it apart, I'm writing this as 30 plus 4 minus 10 plus 8. That's what I'm doing. But I'm seeing that this subtraction goes through because I want to make sure I subtract both the 10 and the 8.
Oh.
Yeah. So it's just a notation to remind yourself that we're subtracting. It's okay? Okay, the last one is another one that we saw a version of. It's called equal additions, and we saw this happen as well in the addition section, but it looks again a little bit different here. So this is 834 minus 158. Okay, so when we saw this before with subtraction, what our goal was no borrowing, no carrying, right? We didn't want to have to regroup and carry. So the same thing is here. The goal is no borrowing. We'll write this one this will be our last one for today. Our goal is no borrowing. So what that means is I want to be able to subtract without having a smaller number on top. So right now, if 4 is over an 8, that's no good. I don't want 4 over 8. I want it to be something that when I subtract, I can just do it without having to regroup or borrow. So how do I do that? Well, the easiest way to do that here is to get that 8 to be a 0. So if I added 2 here, and I added 2 here, then I won't have to do regrouping because I will get 836 on top, and I'll get 160 on bottom, and look at that, 6 minus 0. So I don't want any borrowing, but I really don't want any borrowing because I've turned things into zeros. That's really what it is. Now I don't have any borrowing in the ones column, but the tens column still has borrowing, right? It's got a 3 and a 6. 3 on top, 6 on bottom. No good. I want to change that 6. Well, I can change that 6 into a 0 by adding 40. And if I add 40 on bottom, I have to add 40 on top. So 160 and 40 is 200. That's a lovely number because it's got 2 zeros in it. 836 and 40 is 876. And this is the point when I don't need to keep doing any turning in things into zeros because I can subtract right now, straight down with no regrouping. And at this point, you can even subtract from left to right if you wish, right? Because there's no regrouping, it doesn't matter. So I could do 8 minus 2 is 6, 7 minus 0 is 7, 6 minus 0 is 6. And I get 676. All right, we will pick up there next time.